Hello, everybody. It's really great to be back here in Berlin for CCC. It's been a long time since I've been able to make it here. Previously, I've always been around this time preparing for another conference, CES, but I'm done with that now, thank God. And it's really good to be around so many really brilliant people. It's very humbling. So thanks for having me here. Today I'm going to talk about an implementation of a man-in-the-middle attack on HDCP. And the device that we use for the attack is actually being used to overlay Twitter feeds on top of an HDMI feed that is going to the projector. And of course, I had trouble setting up just a moment ago, but it seems to be running now. If you tweet to Bunnie Studios or 28C3, you should see your comment going across the top, provided that Wi-Fi doesn't fall over. So, that being said, let's get started. First, I guess, what is HDCP? It's the high-definition content protection. It's a pixel-level encryption operating on the link layer. And the cipher structure is a little bit odd. It's a stream cipher. It generates 24 bits of pseudo-random data per cycle. And internally, it has a structure of a pair of block functions that run once per clock cycle. There's a LFSR-based key scheduler, sort of, that whitens the block functions at the beginning of every horizontal retrace. And the block functions themselves are initialized with a bunch of different things, including a 64-bit initial vector that also evolves during vertical blanking intervals. The interesting thing about HDCP is the key management component. They use a key management system that allows you to use distributed private keys with some sort of key revocation on it. It's pretty weak. A public key, in their parlance, is called a key selection vector. And it's a 40-bit number consisting of 20 zeros and 20 ones. The private key is a vector of 40 56-bit numbers. And there's a dot product between the two that generates a shared secret. All of the private keys used in the system are derived from a master key consisting of a 40 by 40 matrix of 56-bit numbers. The master key was leaked about a year ago to this day, and it can be computed directly from a collection of private keys they recovered, perhaps from a set of video cards as shown here. I had nothing to do with it. But thank you to whoever did it. It's actually been a lot of fun for me doing this, and a lot of respect to the people who did it. So why HDCP in the first place? Why would someone want to use it? Well, I don't want to use it, but why do people put it into different things? The idea is that they want to be able to encrypt video transmissions. They want to create a studio to your TV set, fully encrypted path, right? So it complements ACS, BD+, another encryption technology to create the studio-to-screen cryptographic chain. However, that chain was broken a long time ago. ACS was the weakest link. People can rip out movies all they want. So it turns out that when the HDCP master key was released, it was a little bit of a no-op because from the content access standpoint, because people already had access to the content through other vulnerabilities. And it's also possible to build strippers based upon legitimate HDCP keys that have been available for a long time. Basically, people take out an HDCP receiver chip and then just hook them up to the LCD port or some frame buffer, and they can get the data they need out. So the master key itself, from the content manager standpoint, wasn't big news. But so then the question is, why would I bother to try to implement this man-in-the-middle attack on HDCP? And it's all about control, right? At the moment, broadcasters and studios control your screen. You actually don't really get the right to manipulate the video that is being broadcast to you because the DMCA makes it illegal for you to decrypt the video to allow you to manipulate it. So there's this sort of control war going on over who can put something on your very own screen. And it sort of irritates me that I'm not able to go ahead and modify my data within my own home because of some technicalities due to the DMCA. So just an overview of the things that are restricted. If you want to do like a picture-in-picture from 2 feeds, that's not possible because of HDCP. If you want to do content overlays, like what's happening up here, that would not be possible. If you want to do filtering and modification of the image, that's not possible because it's all encrypted. And as a result, there's actually very few commercial HDMI video mixing solutions that can operate on broadcast and movie content. So the goal of implementing the attack is to allow consumer-side content remixing. So the idea is that we want to be able to add web content, internet content to existing TV, live comment and chat. So if you're watching your favorite program, you can tune into a Twitter feed and see what people are kibitzing about. Over-the-top advertising, so you could imagine, based upon some algorithms, to be able to detect an ad and eliminate them, or replace them with entirely new ads that are more targeted to you. You can do interactive TV, so we can add interactive elements to broadcast TV. And another goal of the project was to be compatible with any TV, hence the name any TV, but also net TV. So that's the goal. The question is, how do we do it? That's what I'm here to tell you about. So this is a bit of a eye diagram, but it's sort of this outlines the overall sequence of events and sort of also includes what the NATV does. On the left here is the video source, so there'll be your set-top box, or your Blu-ray player, your PS3, whatever it is. This is a video sync, so this is your TV set, basically. And there's a set of handshakes that go back and forth, and down here I've put the man-in-the-middle attack box that's sitting on the link. There's a set of steps here, A1, B1, B2, C1, basically that go step by step for the handshake. And then here is a corresponding set of things I do while the handshake goes on to intercept it and do the man-in-the-middle attack. So the first thing we do is, what is interesting? We read the device capabilities. Actually, not what we do. What the set-top box does is it queries the monitor and says, hey, monitor, what are you capable of doing? So we'll talk about that step first. This one is important to also man-in-the-middle. Because it's a single bus called DDC. It's basically I2C over HDMI. And it's shared between 2 functions, the monitor capability identification and the key exchange itself. And there's 2 things that we need to do. We need to snoop it, and we also need to squash it. So snooping is easy. You just sort of watch the key exchange and see the bits go by. The squashing is a little more complicated and interesting. With squashing, you basically want to force the TV to have the characteristics that we only support. The reason is that there's some TVs that have 3D TV, some TVs do some strange scan modes that we don't support, and we would like to have this work as sort of a seamless consumer experience. So we actually rewrite the EDID record on the fly as it's negotiated back and forth between the TV and the set-top box. So this is a circuit that enables the snoop and override. This is a standard sort of I2C circuit here. You have a driver, you have a receiver, you have a pair of pull-ups. And then on top of it, we have the snooping of the clock is easy. You just listen to it. And then snooping of the data is easy. You just listen to it. And then to override the data, because it's open collector bus, this is easy. You just have a pull-down transistor. And to override the 1, you essentially have to override an active 0 driver, so we put a big wonkin FET on there. And we have a little bit of a current limiting resistor, so in case they're both on at the same time, you don't burn out the board. It works, we can go into more details later as to how it affects reliability, but in fact, it shouldn't have any impact at all upon the reliability of the link. Now, in order to do the snoop and override, the implementation uses a highly oversampled I2C implementation. So I2C itself is very slow, 100 kilohertz clock. We oversample at 26 megahertz, and basically whenever the clock transitions, we have a small window where essentially we can say, whoop, we didn't want a 0, we want a 1, and we actually switch around so that by the time the next edge comes along at the sampling window, the data is what we want it to be. And the way it works in terms of the protocol level is, we're listening basically only here at the address phase. And then we decide on the acknowledge bit if we want to go ahead and override the data. So we say, OK, you're reading this particular part of the record. I don't care. Let it through. You're reading the next part of the record. I do care. I want to squash 3D TD capability. I go ahead and I rewrite the record on the fly. So this allows me to basically change only the bits that need changing during the monitor identification protocol. Also, we override the hot plug bus. So there's a little wire that is used to detect when you actually plug in your TV set. And the hot plug bus also has a FET on it, so we can go ahead and simulate the cable being unplugged without having unplugged the cable. This is important because basically the hot plug kicks off the whole state machine again for resynchronization and reloading all the records. And so we do this a couple of times, particularly on boot, to go ahead and manipulate all the EDIDs and all of the key state. So back to the diagram again. Now that we've gone ahead and we've intercepted and modified the basic handshake of capabilities, we now have to intercept and listen to and do something with the actual key exchange. The key exchange is a pretty simple set of steps. The link controller goes ahead and writes a 64-bit random number initialization vector, and then it sends over its public key and it reads back the public key. Once the public keys are exchanged, you initialize a cipher state, and then you go. The man in the middle is again listening, intercepting these the key exchange, and itself goes ahead and creates a shadow ROM of everything that's going. And then we initialize a cipher to have exactly the same synchronization state as this, so that we can, on a pixel-by-pixel basis, encrypt data to the identical cipher state and swap them on the fly. Let's see, is there anything I didn't say here? Right, so getting all the initialization vectors is accomplished with I2C sniffing. And once basically the key exchange is captured, the last write is a defined address that actually triggers an interrupt that goes to the host CPU. This is all done in FPGA, by the way. It goes to the host Linux CPU that then triggers a UDIV event that does all of the math for computing the shared keys. So here's, I like to write out the math altogether because a lot of times I read these equations and I don't get them and they're too complicated. So this helps me think it through. When you're computing the private keys, you basically take K, which is the master key. This is the matrix of 40 by 40, 56-bit numbers. And you do a dot product with the public key, and you can get essentially a vector of 40, 56-bit numbers, which is the private key vector for the source. And then you basically take the transposition of the master key, multiply it by the other public key, and you get the other private key vector. This is done by the Linux host computer. And basically, once you have these private key vectors, we then multiply back again by the key selection vectors to derive the shared secrets. The shared secrets should be identical. I compute both to make sure we haven't got corruption on the line. And then after the shared secrets computed, we're good to go on the ciphers. So the ciphers themselves, it's, as I had mentioned earlier, once you plug it into the hardware and you initialize the key schedules, the cipher state has to evolve based upon pixel clock first, but then also on HSync, VSync, data guard band timings, and a bunch of other bits and pieces. So in fact, when you have a frame of video, this is a frame, the active pixels are here, and then there's overscan on the edge for the HSync and VSync periods. They actually only turn on the encryption for actual data, right? So if you actually don't synchronize the cipher state and turn it off when you're not transmitting video data, your cipher gets unsynchronized and you get white noise at the back end. So we have to basically build a system that also passively observes the guard bands, the sync patterns, and so forth. Those are all unencrypted, and align our cipher state. In addition, the way that they do audio transmission and other things inside of HDMI is they have these data islands that are hiding inside the sync areas, and they're marked by a special coding region. And once those happen, you know the next 16 or 32 clock cycles is a data island. And so we have to essentially extract all that timing and use that to synchronize the cipher state. So again, this is sort of a recap of how the pixel by pixel swapping happens. Here is sort of our encrypted video. I sort of hash over it to indicate it's been XORed. It's like the number 1. Goes over a cable. We synchronize pixel by pixel, and then any TV will just go ahead and render only the portion of video that we really want to swap out. It encrypts it with a synchronized cipher, and then it just takes those and swaps those with the pixels that I've encrypted. And then on the TV side, when you decrypt it, instead of getting the number 1, you get the letter I. Basically, that's how the overall system works. So that's all the sort of the math and the crypto stuff. The actual implementation is much more hairy. There's a lot of like real-world stuff you have to deal with, so I'm going to go into a bit of that. The overlay pixels need to be exactly timed to the video pixels. And the overlay itself, so for example, this stuff that's coming across the top here is all being computed by the local Linux computer that's on any TV. And those look like dev-fb0. We're just writing dev-fb0 with WebKit to create this, overlay. There's a bunch of challenges to doing this. The Linux interrupt jitter for frame sync is way too high. You can't just use that to synchronize frames. The local oscillators also drift over time. So up to hundreds of pixels per frame is allowable within the ppm spec of the local crystal oscillators. And if we don't have absolutely tight synchronization, you would see the overlay sort of jittering and looking very nervous on the screen. So there's a few techniques we use to synchronize the frame buffers. First, we don't use the local pix clock to clock the LCD controller on the SoC. We actually take the pix clock from the incoming video and feed that back into the processor and say, here's your clock for that. So that gets rid of entirely all of the clock drift issues and PLL drift issues that you can have. It's something that's a very convenient thing that helps solve a lot of the problems. The next thing we do is we listen to the data going by, and we have to derive all the timings dynamically from the video, and we set the frame buffer properties to match. So on the fly, we listen, we say the sync is this long, the video is this wide, and this high, it corresponds to this CA mode, and then we program our frame buffer to match that. So of course, we don't do that programming right. If you even off by 1 pixel, the frame starts drifting with time. And this, you would think, would be something that's actually quite easy to do, but in fact, a lot of vendors have buggy implementations. They're not actually CA compliant, so you really have to just measure and use heuristics to try and make it bug compliant with all the weird equipment out there that doesn't actually quite work the way the standard says. The other thing is that when the LCD frame buffer starts as a DMA, we basically trigger that with an interrupt based upon the vsync from the video stream. But as mentioned before, the interrupt latency of Linux is quite long and it has a lot of jitter. So there's about 8 lines of elastic buffer within the FPGA that allows us to absorb the jitter. And we have a system that actually tries to measure the interrupt delay between when the interrupt edge arrives and when the actual DMA starts, and we actually pre-compensate that. So we actually start the LCD DMA a little bit earlier so that the first pixel arrives when the actual first pixel comes in the frame. So there's a whole bunch of bits and pieces and stuff that we do to get that to work just right. So the way we do the overlay over videos, we use chroma key. Many people know it, but I'll go over it here in case you don't. If I were to turn off the overlay, you would just see a big pink screen like this with just the data that you want to overlay. Essentially, every color that is magic pink, F0, 000, F0, is swapped with background color. It's a little bit tricky in some spots to do this because you have anti-aliasing sometimes turned on, and the pink will bleed into your images and so forth. So you have to be a little careful when you design the content so that the magic pink doesn't bleed and create pink rings around everything. And so this is what the FPGA implementation looks like on the inside. This is a block diagram of it. The HDMI comes in, we deserialize it to RGB. We have the I2C like DDC bus, which is being snooped and squashed. And then we have a local PLL sync that reserializes data. There's a multiplexer here that, based upon the genlocked data coming from the FIFO, is encrypted and then selected on a pixel-by-pixel basis if the incoming data matches the chroma key. That's basically the entire implementation of the pipeline for the device. Now, there's a few optimizations we had to do to get this to work well. One thing is key caching. So every video source sync, when you plug your Blu-ray player into your TV, the shared secret actually never changes over the life of the device. And people rarely replug things in with each other. So even though we can almost compute the shared secret on the fly for most devices, some devices are very fast and they run a little faster than the protocol and they won't catch, and you get like white noise. So what we do is we cache the computed key the first time we compute it, write it to a temporary location, and then we just check it's the same. If it's not the same, then we yank the hot plug line and we reinitialize. The other thing we do is we do EDID caching. This is a little more important because without EDID caching, EDID is the record that describes the monitor's capabilities. You see a double blink of the screen. We do the first blink of the screen to read a value, and then the second blink to overwrite it. And that sort of creates a bad user experience. So we do EDID caching. And so that's the core FPGA. I want to talk a little more about the bigger system picture of how it's all wrapped together and works in practice. There's FPGA up here, which we saw the block diagram of. We use a PXA168, it's an 800 megahertz ARM CPU, and 128 megabytes of DDR2, a micro SD firmware. We have an infrared remote detector, so you can use remote control to control it. We have an OTG connector on it, and we have Wi-Fi on the board. And so, of course, I like hardware, and so I include pictures of hardware. This is the FPGA here. It's a Spartan-6 FPGA. You can see that, in fact, the HDMI pins go straight up in the FPGA. There's no intervening buffers. The Spartan-6 is capable of driving and interpreting HDMI on the fly without any help of its own. Micro SD card, you can swap it with a bigger disk if you want. That's the PMIC, the IR receiver, some status LEDs, must have the blinking lights. This is the Wi-Fi chip, the CPU, and a little boot spinor. And this is an extender because typically you're going to hide the device behind your TV, so you can actually plug in a little infrared receiver on a long wire and put it where you need it to be. The solution is also a complete open stack. So a lot of times, we focus a lot on sort of U-boot to Linux to WebKit and so forth. This solution here, actually, we open source the plastics, the PCB, the FPGA, the Verilog. Of course, the U-boot, the Linux, WebKit is open source. The widgets are open source, they're stored in GitHub. And then we go one step beyond that. We actually give you a provisioning server so that if you were to actually develop your own system, you can actually bring up your own update network and so forth, and a build system on top of that based upon Open Embedded. And I'll go into that a little bit more in a moment. So the application environment for this, this overlay here, and it looks like Wi-Fi fell over, which is why we don't have any more tweets going across. The application environment, this guy here is basically HTML, JavaScript. The CSS template is configured basically to make the background magic pink, so anything you draw over it blocks the screen. The apps are all JavaScript HTML programs, but you can extend it to use anything that uses dev-fb0. So if you use SDL, Flash, whatever it is, you can also use it with this infrastructure. We use GitHub to store all of our demo apps. So every time you reboot the client, we do a git pull, and if there's new widgets or something, it just pulls right down to your device, and you have new widgets on the device. And the firmware updates are also served from an EC2 infrastructure. So we provide an AMI that allows you to replicate this yourself. Another thing we do is we provide an HTTP API. So the events that you saw previously scrolling across the top here are actually, you can actually issue them from any device in the network. We actually broadcast ourselves with a zeroconf, bonjour. You can discover it with a smartphone, for example, and based upon the discover IP address, if you get an SMS on your smartphone, it can go ahead and forward the event to any TV, so an SMS could then scroll across the screen. Basically, this is what an example call looks like. It's just a GET request, and you just and you can send events to any TV. So the idea here is that if you had a smart home environment, or you want to do something where you're overlaying something on your screen, and you don't want to do a lot of work or programming, you just go ahead and you just discover the IP address, and you use HTTP to go ahead and overlay the events very quickly and very easily. This allows you to avoid having to do a lot of coding to get some sort of new system and new functionality. Also, we provide a turnkey build system. We have a public Amazon EC2 instance with a pre-built angstrom distribution. So it's great that you can get source, but the problem is if you want to build the kernel, Qt, X, and everything, you're downloading source for 7 hours, and then you're building for another 7 hours, and then you find out it doesn't work, you misconfigured something, and then you're waiting another 7 hours to just get going. It's a big pain in the butt. So what you can do is you can essentially just go to Amazon and then use our public AMI, and it comes up, and essentially it's like we handed you the keyboard from our dev environment, and you can just go from there with a pre-built image. It comes with a local Git repo and build bot. So basically, you can go ahead and go to our AMI, go to Amazon, launch it. You can go ahead and commit your code to the local Git repo on the inside. And when you do a code commit, it goes ahead and automatically triggers a build for you, so you can watch your builds going and so forth. And then at the end of the day, there's a set of images that are generated for you that are served via web page from the server. And so there's a big binary file here that basically you need to download that once, burn it on your device. But once you've downloaded that and burned it on there, the device is keyed to go back to your server for updates. So then code development becomes not, code something, SCP it on, and run it. You just simply just do a push, git push. It does the build, and then through O package, it triggers an update, and your stuff just ends up on your device. And this is something that you can just get without having to do a lot of work. So we call it like 30-minute sort of running start. We want to get developers going on the platform without having to do a lot of mucking around with cross-compilers and so forth. The hardware is open. I'm a hardware guy. I like hardware, so of course I'm going to include the porn for hardware. This is the case design. It's done in SolidWorks. You can download and look at it. I put graffiti on the inside and bits and pieces. It's made in steel tooling out in China. I love the way it looks and the way it smells. It's true. If anyone's ever seen me get like a new gadget out, I always open the anti-stat bag and I smell it, because I've been in enough factories you can tell what flux they're using, what processor they're using, and sort of how the weather was in Shenzhen when they built it. That all comes with the box. And the other thing is the Chinese will tell you that you can only use German steel for making these tools because Chinese steel is too soft. I don't know what it is, but they always say we can only buy German steel, and they tell me that as like an advertising thing. So the steel comes from Germany. Schematics are, of course, open online. I designed an LTM. You can get the source files, download them, and play with them. And the PCB layouts as well are available for you to go ahead and browse and modify. So this is a complete open solution that we provided: the hardware, schematics, PCB, design FPGA, the software, a complete turnkey build environment, including everything from top to bottom. So we tried to be very completionist about this. And the goal we had is we wanted to go from half an hour from getting the device to essentially sort of a production grade build environment where you can actually give it to someone else and say, have the device and we can push updates to you and you can actually use it for your own application. And you can get it now actually at adafruit.com. They're actually kindly being my distributor for the product. So just to recap, and I said I'd go fast, and I did go fast. I've demonstrated a HDCP man-in-the-middle implementation. It's a complete solution. We intercept the key exchange on the fly. We derive the shared secrets and synchronize the transmit ciphers. We multiplex overlay video using chroma key. We avoid decrypting data. So if you notice in the entire path, we never actually decrypt data. So I call it DMCA safe. DMCA says it's illegal to circumvent copyright. People say, wow, what are you doing? And I says, well, I didn't circumvent anything. I didn't decrypt anything. So how can you be mad at me for DMCA? And we also modify EDID records to force compatibility. We enable a video compositing function. So if you had an old TV or a legacy TV that didn't have smart TV, you can go ahead and add that to it. You can modify video content now. You can block ads. You can go ahead and show live internet commentary, so on and so forth, on top of your device. And it's a completely open hardware and software stack. And I like to emphasize that it's a non-infringing use of the master key. So there's a sort of legal notion that if you have something that is has only the purpose of only has an illegal purpose, then owning it is tantamount to sort of committing the crime. So if you have a bunch of, like, I don't know, TNT in your backyard, then they think you're a terrorist, right? So prior to this, the only use of the HDCP master key was circumvention, right? And the thing that I like the most about this is that it blurs the association of the master key essentially with privacy. Now you can have the master key, there's a legitimate use for it, it's non-infringing, it's commercially useful, it's been well implemented, it's not a sham. There's a sort of argument that says, well, you have this like kind of like backup use or whatever it is, and then everyone says backup, and everyone knows it's sort of tantamount to something else. This one's a bona fide use, so it helps sort of legitimize the distribution and existence of the master key. So thanks for your attention. I'll take questions now. I guess down in the front there.
Okay, normally you would queue up, but I'll make an exception for you.
Hey, Bunny.
Hey.
So given that you're not doing, you're doing pixel by pixel substitution, is there a limit with your FPGA and your processor on how many pixels you can substitute given the overall screen resolution?
Right, so it all happens on the fly, and so the limit is limited by the pixel clock rate of the FPGA. A standard Spartan-6 without the really expensive transceivers is limited to 95 megahertz pix clock, which is a gigahertz line rate, basically. And that corresponds to a 1080i resolution or a 1080p24. It doesn't do 1080p60, which is a common resolution, but you can actually overclock the FPGA, and it actually works most of the time to get to that. But as a commercial product, we block the overclocking, but it's very easily disabled. You could do it yourself if you wanted to.
If you have questions, please try to queue up at the microphones, but we have one from the internet, I think.
Okay, we have two questions. What can this do other than overlays?
What can this do other than overlays? Well, so the UI you see here is it's a WebKit browser, right? So it's a little bit tough in this environment for me to do the demo, but basically there are Android apps and iPhone apps that work with this, and I can take pictures and share them on the screen. So just sling the picture to the screen, and you can also enter a URL and view a web page on the screen as well, or anything else that you can do. Imagine coding with JavaScript, HTML, right? This is just sort of like an example demo that we did, sort of to give you an idea of flavor, but it's not actually the final thing. It's really up to you guys to tell me what you want to do with it.
Okay.
Right.
Yeah, and another question. Sorry. Why don't you hook up your own EDID?
EDID, yes.
Okay. Or read the original and provide the modified copy from the controller?
Can you say that one more time? I didn't quite understand it.
The whole question or the last part?
Just the whole question. Why don't I hook up
your own ID?
Oh, EDID. Okay. Why don't I just go ahead and blast like a generic EDID in? Okay. Because not every TV is a 720p or 1080p TV. There's some really crappy TVs out there. You can damage them. Like if someone actually in the world had a CRT, right, and they weren't very careful about it, and we actually overdrove the sync, you could burn out the tube or something. So we have to read the monitor's capabilities and respect that, and then deselect the modes that we don't allow. That's why we do the overriding.
Okay, and the last one. How complicated would be to use your own hardware to decrypt the HDCP?
Right. How hard is it to decrypt HDCP? I knew that question was going to come. There's for strictly legal reasons, there's a substantial barrier that I've put in to decrypting, but it's not like an impossible barrier, it's more like an effort barrier, right? So for example, this device here, the actual device itself has the master key, but it has no actual public key of its own. It must borrow the public key from a source and a sink for it to work. It actually checks to make sure you have a properly licensed device on both ends of the link. And that's for another legal reason. You want to make sure that you're following all the licensing rules and so forth to do this. In order to have it actually just decrypt on its own, it needs to provide its own public key. Someone has to put that in there, right? That's possible to the extent to this crowd. I mean, there's many smart people who could do it, but a regular consumer could not easily go and hack the Verilog to do that. So it's theoretically possible, but there is, at the same point, for legal reasons, I made sure there was at least a barrier. So it's not like one of those like clip here and you have like a radio that can listen to like radio bands or something like that, which would create sort of a blurring of the line of the legitimacy of the product.
Okay, question over there.
Hi there. How many people have been working on this pretty impressive piece of hardware, and how long did it take to actually develop and build it?
Okay, so the question was how many people are working on it and how long did it take? This hardware was designed in Singapore. I moved there about 1.5 years ago. We conceived it about last year this time, had just some sketches, showed to people, see what they thought. We did a stretch card, so basically just the FPGA itself, and we plugged it actually into the LCD port of an existing Chumby device that we had at the time, and just demonstrated the overlay in May. And then we finalized the boards and did the tooling and so forth. We had production by October. And basically, we've been now going through sort of the process of getting out to distribution. We had a team of, I think at the biggest point, it was about 5 or 6 people working on it. Very, very talented people. I'm really lucky to be working with them. And most of them are software guys. Actually, all of them are software guys. I'm the only hardware guy on the team. So the hardware, the case design, the board layout, the board bring up is done by me, and then the rest of the guys do all that really insane stuff with the build system and Linux and the software bits that I don't get quite so well. So.
Okay, another one over there.
How full is the Spartan, and have you enough room to do a full alpha mixer instead of chroma keying?
Right. The Spartan's at 87%, which is pretty full as far as FPGAs goes, but it's got some space. There's stuff you can strip out, so a lot of it is the line buffers. It actually turns out we don't need 8 lines. You get away with like probably 2 lines in most cases, so that would actually free up a lot of resources. Alpha blending, if you are willing to just outright decrypt the data to do the alpha blending and then re-encrypt it, is actually trivial to do. It's just a very small path. It wouldn't take much data. There's some very smart guys here at this conference I've been talking to have given me really good ideas on how to do it without ever decrypting the data. I haven't implemented that fully, but we're gonna give that a try and see if we can do something there. But it should be able to fit.
Okay, another question from the internet, and then over there.
Okay. How would it be a footprint compatible replacement to use the Spartan-6 parts with the high-speed transceivers?
Okay, yeah. So there's the question: can we put the T-series Spartan-6 in that has like the gigabit transceivers that lets you do 3D TV and stuff like that? So unfortunately, Xilinx did not make them footprint compatible. You actually have to relay out the board between the two. And that's a difficult, so there is a part you can drop in that would allow you to do 3D TV standards and so forth, but it's like $50, right? The current part I have is like 1/10 that cost. So the feeling I have is that the market wouldn't bear the cost of just that much added cost to the device, so we decided to use a much lower cost part. There's a thought that we'll do like a pro version or a higher end version with for people who are willing to pay that much more money for a device. But it would require a full respin of the PCB and so forth to do it, and a lot more money.
Okay, 2 questions over there.
The sliding up of the overlay, which could be seen a few times during the talk, is it an artifact from the overlay going out of sync with the video feed, or what is it? And can it be alleviated, or is it just there?
Yeah, no, that's the whole, as you saw, I was struggling a bit with the demo here. There's a bit of a hack going on here. It's going from a display port to HDMI to overlay to a VGA converter, and then so on and so forth. So somewhere along the way, the sync is getting a little corrupted, And when I lose VSync, it rolls a bit, just like you would always roll if you lose VSync on a TV set. I think if I didn't have this VGA converter in the middle, it would be much more stable. I never see it on a full digital link, but yeah, that's my guess as to what's going on.
Is there another question over there? Okay, then we have another one from the internet and then there.
Okay, this is a long question. I will try to make it short. How difficult would it be to adjust the FPGA part to make this part of OSS drivers for those commercial available hardware for HDMI capture?
I had trouble understanding how difficult it is to write what kind of driver?
OSS.
OSX drivers. So
Yeah.
you want to write OSX drivers for what purpose?
Okay, I must say the question. There are commercial available HDMI captures interface. Unfortunately, there are no OSS drivers for this yet. How difficult would it be to adjust this FPGA part to make this part of OSS drivers for those commercial available hardware for HDMI capture?
So basically, how difficult is it to take this hardware and turn it into something that does HDMI capture with OSX? I think.
No, it's about OSS, open source software.
Open source.
The question
Software.
seems to hinge on the fact that there seem to exist FPGA to PCI express boards that have an FPGA and an HDMI connector and a PCI Express connector.
Right.
And he wants to know how difficult it would be to adjust your approach to basically run on the FPGA in these existing hardware boards.
It should be easy, I think. I mean, the Verilog is open source, right? So you can get that and compile it, and the interfaces are there. So if you had an existing dev board with PCI Express and 2 HDMI ports on it, you just have to map out the pins and get it to compile. It's SMOP, I think.
Okay, then there's a question.
Hi, is it possible to split one source to two different or more different videos, TV sets, and what about merging audio?
And what was the last part of the question? What merging what?
Audio, because HDMI is also possible to transmit audio signals.
Oh, audio, yes, okay. So the first part, I believe, was asking, can you split it to 2 different outputs? Yes, you can. I mean, the board itself doesn't have the second port on it, right? And so one of the limitations of the chip I have is I've now saturated the number of LVDS outputs I have, and so you have to go to higher-end chip. But if you want to just replicate to n different ports, that's actually quite easy. That's not hard at all. You just have to pick which one is the master EDID that does the transaction and handshaking, and the rest of them slave off of it. And it also assumes they're not unencrypted, because each device will have their own key. So if it's all encrypted, you can only go to one. As for audio, the wires are there to do audio. It's a firmware update, just a firmware update to do audio. I haven't. Audio itself is a little more complicated because there's CRCs around the audio and some clock adjustment drift and so forth. I haven't gotten through and put all the code to do audio, but that's one of the things that you should be able to do in the future, is to be able to overlay audio as well, inject audio.
Okay, is there another question from the internet, or are we done now? Okay.
Why don't you use the ARM?
Why do I use an ARM?
FIQ to avoid the Linux kernel RIQ latency?
Oh, okay. When I use an FIQ, I don't know. It was hard. It was harder than the way I did it, right? I think I seem to remember. So a lot of the kernel stuff was done by some of the other guys I work with, and I help with that. But I think the explanation I had was that we had to do a lot of tweaking on the existing kernel to get the FIQs to work, and it would be difficult. And so it was easier for me to do something in hardware to wrap around it. And so that's what we did.
Okay.
It's a hardware problem.
I I may speak to that. I also had some similar problems, and the FAQ also has some latency, so that's not even completely foolproof solution.
Yeah.
Even then. Okay. Any more questions from the audience or the internet? Otherwise, we seem to be finished.
Yes.
Give a warm applause to Bunnie.
Thank you.